So in this Excel example for contingency table, we're going back to the same example we did previously, which is you have the three hotels, and then that's your dimension for the column. And the dimension for row, the categorical variable for the row is what is the reason for a guest not being satisfied. So you have two categories earlier. That was the guests who are satisfied says that they will come back, and then guests who say no, we're not going to come back. Okay, so now you want to look at those people who say that they're not going to come back. So primary, so and then you look at what is the reason, why are they dissatisfied. So primary reason for not returning has 1, 2, 3, 4 possible reasons. Okay, so row dimension, okay, or row categorical variable is reason for not returning. The column categorical variable is the hotel. Okay, so you have 187 randomly selected guests who have expressed a dissatisfaction with the hotel, and here is the observed frequencies in terms of the reasons given. Now we want to test whether the reason given for not returning is independent of the hotel. So it doesn't matter which hotel. Okay, the reasons are all over the place. Or is there a relationship? If there is a relationship, then maybe there is something more for us to study to see which hotel is doing badly in which area. So we want to see whether they are independent or not. So let's head on over to Excel. So first let's define the variables. The categorical variable for column, that's the hotels, and these are in 3 levels. And for the rows is the reason for not returning. And contingency table hypothesis is always the same. Null hypothesis is always they are independent. An alternative is always the two categorical variables are dependent. Okay, and we will use an alpha of 5%. Okay, now here is the sample that we have taken. Let's look at the sample observations. So these are the number of guests expressing concern for the reason for not returning from the 3 different hotels. Now you sum the row. Okay, put the border back. So here if you sum the column, okay, so now that's our n. So it's the total sample size. Okay. The expected frequencies for each cell would be the row total. So row total must come from column F. So you have to use the relative cell address judiciously. I will be looking for that. Okay. You should not set up individual formulas for each cell separately. You have to set up formula for one cell and copy it across. So here F is fixed. Row must change from 31 to 32 to 33. So dollar should go for F. And then column total, and column should change. Row should be fixed at 35. And then divide by the sample size, and sample size must always come from that single cell. So the dollar sign should go for both the column and the row. Now this will give us the expected frequency for one cell properly set up with absolute references so it can be copied. Okay. When you do your homework, I will be looking for that. If you set up these formulas individually cell by cell, I'll be deducting huge amounts of points for that, because the whole point of relative addressing is to keep the computation, the formulas that you have to enter, to a minimum. So now let's double check that our computations are error free, which means when you sum this way for each row, you should replicate what we have in the observed frequencies. And when you sum the columns, again it should match the sum of the observed frequencies. The sum for the observed frequencies are there. Okay, so they all match, so the computations are valid. Now we can set up our chi-squared will be observed frequency minus the corresponding expected frequency. Okay, square that and you divide by the expected frequency. Copy for the rest of the cells. And you sum them and you have the chi-squared stat. Okay, and for this to work, of course, remember you have to make sure that all the expected frequencies are 5 or more, which is so in this case. So all expected frequencies are greater than or equal to 5, so large sample requirement is satisfied. Okay, number of rows is the number of categories in the row categorical variable. So use count A for counting alphanumeric values, then count A for the columns will give you the number of columns. Okay, and the degrees of freedom then is r minus 1 times c minus 1. So let's change that to general format. Then our chi-squared will be chi-sq-inv dot rt of alpha comma degrees of freedom is 6. So that will give us the chi-squared table value, and if we are to use the textbook for this, we have 6 degrees of freedom, alpha of 0.05, which is here the upper tail, which is 12.592. That's what we have here. So our chi-squared stat exceeds the critical value, so we reject the null hypothesis. So which means there is a relationship between the reasons given and the hotel. Some hotels have some reasons, the other hotels have other reasons. So we can divide. We cannot have the same approach for all the hotels. The approach to alleviate the problem or solve the problem of guests not returning, you have to have different approach for different hotels. Now p-value, you take the calculated stat comma the degrees of freedom for chi-squared dot this dot rt. That gives you the p-value of 0.012%. So p-value being less than 5%, we reject and provide an interpretation. So we have sufficient evidence to conclude that the reasons given for the guest not returning is dependent upon the hotel. And the probability that we are wrong, making type 1 error, is 0.012%.